Hello, welcome back to my channel Study with me. This time I will explain subtopics 1.3.6 and 1.3.7 about ionization energy. This is higher level content under structure 1.3 first theme. Please join my WhatsApp and Telegram channel as I'm planning to create a dedicated IB chemistry community where we can have live classes, a place for you to post your questions, and I will work through them with you. Once we have a good number of students, I'll officially launch the community. And also please share this channel with friends who are also studying IB chemistry. The more students who join, the more opportunities we'll have to grow and support each other in our studies. Okay, from these subtopics, you need to know how to explain the trends and these continuities in the first ionization energy across a period and down a group, and calculated the value of the first ionization energy from spectral data that gives the wavelength of or frequency of the converged limit. And this formula, the value of the Planck constant H and the equation are given in the data booklet. And also from another subtopic, you need to know how to deduce the group of an element from its successive ionization data. These are formula you can find on the data booklet. Okay, C equals to frequency times wavelength, and the ionization energy equals to Planck constant times frequency. Right. Here is the figure about transitions of electrons from n equals to 1 to n equals to infinity. Right, at the convergence limit, okay, the lines, these lines merge or converge to form a continuum. Beyond this point, the electron can have any energy and so must be free from the influence of the nucleus. Okay, so outside of the atom, it means the electron has been removed, so means the atom has been ionized, right? So this represents an energy change from n equals to 1 to n equals to infinity. So knowing the frequency of the light emitted at the convergence limit, it enables to work out the ionization energy of an atom. This is to calculate the ionization energy, okay? Planck constant times frequencies, or we also need the frequency. We also can calculate the frequency when the speed of light and wavelength are known, okay? And when we combine these two formulas, we can get Planck constants times speed of light divided by wavelength to calculate the ionization energy, right? Speed of light, the number, this constant, it is given on the data booklet, the same with Planck constant. You can see on the section 2, this is the Planck constant, and this is the speed of light, okay? Let's calculate this. So the frequency of a line in the visible emission spectrum of hydrogen is 4.57 times 10 to the power 14 hertz. So this is the frequency. Calculate the energy of the photon. Frequency is known. Planck constant here. So you can calculate energy equals to Planck constant times frequency. So 6.63 times 10 to the power negative 34 times the frequency is 4.57 times 10 to the power 14. The answer is 3.03 times 10 to the power negative 19 joule. If the frequency of the convergence limits in the Lyman series, so frequency is 3.28 times 10 to the power 15, calculate the ionization energy. So it will be the same way. Planck constant times frequency, 6.63 times 10 to the power 34 times the frequency, 3.28 times 10 to the power 15. then you will get 2.17 times 10 to the power negative 18 joules. Okay. Spectral lines converge at 9.12 times 10 to the power negative 8 meter in the emission spectrum of the hydrogen atom. Calculate the first ionization energy of hydrogen in kilojoule per mole. So to do the calculation is ionization energy equals to H times V. But we don't have any frequency here. Remember, we have another formula. C equals frequency times wavelength. So C equals frequency times wavelength. So this is the wavelength. And C is a constant, 3 times 10 to the power 8. So we can calculate the frequency. So 3 times 10 to the power 8 to the power 8, and then wavelength 9.12 times 10 to the power negative 8. So frequency would be 3.29 times 10 to the power 15. So we can do the calculation here. So Planck constant is 6.63 times 10 to the power negative 34 times 3.29 times 10 to the power 15. Then you get 2.18 times 10 to the power negative 18, the ionization energy. Okay, first ionization energy. Ionization energy means the amount of energy that is required to remove an electron from a gaseous atom. So after a gaseous atom, we remove an electron, we produce a cation, +1, because one electron is removed. So it is called first ionization energy. And then we move the second electron, produce X2 plus, right? That energy that is required to remove the second electron, called second ionization energy. And the third electron called third ionization energy. And the fourth electron is called fourth ionization energy. The second ionization energy is higher than the first one. The third is higher than the second one. The fourth is higher than the third ionization energy. This is due to the attraction forces between the nucleus and the electrons that are left. Okay, so when we remove the electron, the first electrons, it has a greater repulsion. This causes easier for you to remove the electron, and also the electron is a bit far. It's quite far from the nucleus, right? Because this is the valence electron and it is located on the last shell. Okay, and after we remove one electron, so the repulsion becomes less. So like in this figure, therefore the attraction between electrons and the nucleus becomes stronger. So these electrons will be pulled closer to the nucleus. So you need more energy. After you remove the second electrons and then you want to remove the third electrons, again the repulsion becomes less and then the attraction becomes even stronger. So you need more energy to remove the third electron. That's why the fourth is higher than the third is higher than the second is higher than the first ionization energy. And this one also is affected by the atomic radius, right? So when you remove the electron and then the radius becomes smaller, so the attraction becomes bigger. All right, successive ionization energy. Okay, so it's potassium with the number of electrons 19 and the electronic structure is 2881. So we remove the first electron as the valence electrons on the last shells, right? So the ionization energy is very low because it's very easy. I mean, you don't require that high amount of energy because it's the valence electron. And when we remove the second electron, there is a large jump between the first and the second. Okay, as you can see, after you remove this one, so there is no more these shells, right, for example, And now you move to the third main energy level. So it's a different energy level. That's why there is a high jump. And look at here. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. So after you remove this one, and now when you remove this one, this electron, the 10th electron, there is again high jump. So actually you remove one of the electron from this shells, the second main energy level. And if you remove again this, you move to this shell, so there is a high jump. So this the big gap, the large differences in the ionization energy shows you the number of main energy level. So there is 1, the first energy level, and that main energy level, 1, 2, 3, 4. So it has 4 shells, and it's correct. So 1, 2, 3, 4. So the successive ionization energy actually can also help you to determine what kind of element, which element is down the periodic table. So you calculate how many electrons, so that's how you will know which element, and you can reconfirm or reassure which element by looking at the how many main energy level, by looking at the jumps between the one energy level to another energy level. So you actually can determine the period, okay? And the first, how many electrons that are easy, like in the beginning, this will determine which group. So you can actually find out what element is that through the group, this figure, Okay, so for this one, right, you can actually see the other large jumps on active inspire. So there are large jump in energy when we remove from a new lower energy level, okay, a new lower energy level to the closer to the nucleus. So this supports the existence of the main energy level. And large jump indicates group number, the electron number removed before the jump. So as you can see here, this large jump, this one. So we see Na from this to this. So the first electron is easy to remove. Mg, the first 2 electron do not require the high energy to be removed. And the first 3 electrons, because Al has 3 valence electron, Mg has 2 valence electron. The same thing as well for Si. 1, 2, 3, 4 comes from group 14. So the first 4 electrons do not require high ionization energy. But the 5th one is quite high because you already moved to another main energy level. Okay? This one, let's determine what is the element from this figure. Okay, so this one is 4, this one is 8, and this one is 2. So the electronic structure is 284. It has 3 main energy levels. So period 3, and then group, which one is the easiest one, which electron? So this 4th electron. So group 14, right? And the number of electron, it's 14. So let's look at to the periodic table. Period 3, group 14. Period 3, and then group 14. Period 3, group 14. Okay, and the valence electron is 4, number of electron is 14. So the element is silicon. So this one is silicon. And then this one, okay, so this one, it got 5, the first 5. So valence electron, it's 5, and then this one is 8, This one is 2. Period 3, group 15, number of electron is 15. Okay, so what element is that? Phosphorus. Period 3, group 15, number of electron is 15. Right? So that's how actually the figure or this graph can help you to determine what element, which element is now on the periodic table. Okay, so this is the trends of the ionization energy, okay, across period and down a group. So as an atom increases size, right, increases size from lithium, okay, so lithium to rubidium, okay, they comes from group 1, lithium, sodium, potassium, and rubidium. So the number of shells, so period 2, number of shells 2, and then period 3, number of shells 3. So number of shells increases because of the number of electron increases. Therefore, the attraction between the nucleus and then the valence electrons getting weaker, so it's easier to remove. So when you move down a group, to remove the electron become easier because the attraction forces becomes weaker due to the largest atomic radius. Okay, we can see here reduce. And then across period, this we can also see on the, for the down a group from HE to XE, this is group 18, reduce, right, down a group. And now for this, okay, Li to Ne, Li to Ne across period, you can see increases, down a group decreases, across period increases, because when you move across period, okay, the charges increases, so +1, +2. So the attractions between the nucleus and then the electrons become stronger because the atomic radius decreases. We will talk about this actually relationship between atomic radius and ionization energy in the next videos. So for now, when the number of shells, so period 2, they have the same number of shells because period 2, all of them are on the second period. But the number of electrons increases because of the number of protons increases, and number of protons, actually the influence comes from number of protons and the charge. So number of proton here is 3, here is 4, 5, 6 until 10. So this will cause greater attraction forces, and the charge also increases, +2, +1, +3, right? So the attraction between the electrons and the nucleus becomes stronger. Therefore, it's difficult to remove the electron. That's why across period, the ionization energy increases, but down a group decreases because the attraction forces across period getting stronger, down a group getting weaker. Okay? Due to across period, the atomic radius getting smaller, down a group atomic period getting bigger. All right? So let's go back to the subtopics. Okay. There are linking questions asking about how does the trends of ionization energy values across a period and down a group explain the trends and the properties of metals and non-metals. Right, so across period, ionization energy increases from left to right. Metal with low ionization lose electron easily, making them more reactive, while non-metals with high ionization energy tends to gain or share electrons, forming anions or covalent bond. Na or Mg are highly reactive, while oxygen and chlorine are more likely to gain electrons to form anions or covalent compounds. And down a group, ionization energy decreases, right? Metal become more reactive and it is easily to lose the electrons because the size of the atom getting bigger. While nonmetals become less reactive as their ability to attract electrons weaken, right? Because the most electronegative element is fluorine. So when you go far from fluorine, the electronegativity becomes less. So the attraction for an additional electrons weaken, even they still tend to gain electrons. Okay? And next, how do patterns of successive ionization energies of transition element helps to explain the variable oxidation states of the elements? Okay, between 3D and 4s, when we remove the electrons, remember? We remove the electrons first from 4s and then 3D, right? The difference of ionization energy is not that significant. So the successive ionization energy do not increase significantly to remove the electrons. And the energy is also relatively small, okay, allowing to remove of multiple electrons. That's why transition elements have multiple or variable oxidation states. For one transition elements, for example, manganese, it could be +1, +2, +3, +7. We will talk about this in the next video as well when we talk about the properties of the transition elements. Also, we will calculate the oxidation state, so you will know the real reason why it has variable oxidation states and the relationship with the ionization energy. All right, so that's all for the explanation for this video. So we talk about the convergence limit and then how to do the ionization energy, and so we talk about why the second ionization energy is higher than the first, the third is higher than the second, and then through the successive ionization energy we can also determine which element on the periodic table and the trends in general, the ionization energy across period and down a group. But this will be explained more detail in the periodic trends video. Okay, so thank you so much for watching. If you haven't already, please subscribe to the channel and do not forget to share it with friends who might benefit. Be sure to join the WhatsApp and Telegram channels to stay updated on the community, where I plan to hold live classes, answer your questions, and work through IB staff exam questions for each topic. Your support means everything for me, and see you in the next video.